Hi, this is Jeff West. Thanks for joining us in the 5th installment of our Webcast series for developers. Today we'll be covering troubleshooting and tuning with WebLogic. Here's an agenda for today's session. First, we will cover troubleshooting and tuning in a general sense, and then we will focus on JRocket and WebLogic. After the presentation, we will have a demo of load testing with SOAP UI, monitoring with the WebLogic admin console and JRocket mission control, and then diagnostics with the JRocket flight recorder. Just a reminder before we get started, you can use the form, the Webcast form on the bottom right-hand screen of this window in order to submit questions that we can answer during the session and at the end of the session. So please utilize this functionality if you have a question. Thanks. There are many layers of an application stack that can contribute to poor performance, scalability, or throughput. You can take a top-down approach, starting with your application and move down the stack, but the best approach is a holistic one, where you look at multiple levels of the stack at the same time when you're doing troubleshooting and testing. Many of our customers seem to start at the application server layer because they claim that there's nothing wrong with the applications that they build. Most code written by all developers in the world has bugs and can be performance tuned. And even if you think you have the best developers in the world, chances are there are opportunities to increase performance and scalability in your application code. The ideal performance funnel is one that is not a funnel. It's more like a pipe, but this is not reality. At every layer of the stack, there's a loss of performance, and the task of performance tuning is to minimize the impact that each layer has. Applications that are well designed and built typically bottleneck with I/O, and this is really where you want to be. This means that you've minimized the impact of the other layers of the stack and gotten to a physical limit, not a logical one. In most cases, this is where you'll start. You'll start with an average application running on an app server that has no tuning whatsoever. In this case, chances are the application will be the bottleneck. And this is not an accusation or a transfer of blame. This is just how the process works. First, you have to make your application work right, and then you can make it work faster. Only a very, very mature team of developers will produce an application that doesn't require much performance tuning. And there's many steps along the way. Once you clear one bottleneck, you're likely to find another. Sometimes a bottleneck that you thought you cleared will reemerge or manifest itself in a different way. It's an iterative process, and while you may allocate 2 weeks for performance testing, there's no guarantee that you'll get it all done in that time frame. As a developer participating in performance tuning, this should be your expectation, and you shouldn't lose hope if it takes longer than expected. When you look at Oracle's overall strategy, you see an attempt to get the best configuration, best performance out of the box. We want to control the whole stack, not because we want to control the world, but because we want to be able to do performance engineering and innovation at every level of the stack in order to provide the best performance and user experience possible. Since we own the whole stack, now with Sun hardware, we can engineer systems that would be very difficult, if not impossible, to create if we only had influence over the database application or middleware layer. So enough marketing speak. Let's talk about the tools that come with WebLogic for troubleshooting. There are many tools available for troubleshooting. You can use something like the Windows Performance Monitor, Unix Top, or other commands or packaged software. And when you look at the different layers of the stack, you'll see that there's many levers to pull and variables to consider. When you're trying to find a problem, you typically start ruling out factors at each layer of the stack. Sometimes you can narrow it down and find the problem, and sometimes you can't. In many cases, you find that you have to put a lot of effort to correlate data from different sources in order to get to a root cause. And then sometimes you have to do it over again. What we'll be focusing on today is a set of tools that's available with WebLogic in order to troubleshoot and tune. This set includes the JRocket flight recorder and JRocket mission control. For those of you who are not familiar with it, I want to give a brief introduction of the JRocket JVM. JRocket is a JVM that was created by Appeal Virtual Machines, which was acquired by BEA in 2002. In 2008, it became a part of Oracle Fusion Middleware. It is a proprietary JVM that's written primarily for server-side applications. As such, it is written for machines that have a lot of physical memory and for applications that run for a very long time, so days, weeks, or even years, such as application servers. If you look at the startup time compared with Hotspot, you'll find that in some cases JRocket starts up slower, but JRocket trades startup time and memory for improved performance. JRocket does not support technologies like Java Web Start, but does support Swing applications. Since desktop Swing applications are short-lived, you may find a better experience using Hotspot for these. Now let's get into the weeds a bit with WebLogic. The WebLogic Diagnostic Framework is a monitoring and diagnostic framework that defines and implements a set of services that run within WebLogic server processes and participate in the standard server lifecycle. Using WLDF, you can create, collect, analyze, archive, and access diagnostic data generated by a running server and the applications deployed within its containers. This data provides insight into the runtime performance of servers and applications and enables you to isolate and diagnose faults when they occur. WLDF includes several components for collecting and analyzing data. There is a diagnostic image capture, which creates a diagnostic snapshot from the server that can be used for post-failure analysis. There's an archive that's used to persist data and events and log records and metrics over time. And there are point-cut instrumentations that add diagnostic code to WebLogic server instances and the applications running on them to execute diagnostic actions at specified locations in the code. The instrumentation component provides the means for associating the diagnostic context with requests so that they can be tracked as they flow through the system. We also have an mbean harvester that captures metrics from runtime mbeans, including WebLogic server mbeans and custom mbeans, which can be archived and later accessed for viewing historical data. With watches and notifications, we provide the means for monitoring server and application states and sending notifications based on criteria set in watches. And finally, with logging services, you can manage logs for monitoring server, subsystem, and application events. The WebLogic server logging services are documented separately from the rest of the WebLogic diagnostic framework. So I've mentioned Flight Recorder a couple times, and you may be wondering what it is. The JRocket Flight Recorder is much like the flight recorder or the black box in an airplane that records all of the events that happen in the system. The goal is to be able to use this data in the case of a problem or a crash and go back in time and see what was happening leading up to the problem. It's always on, and it's a circular buffer that only retains a certain amount of data. Even though it's always on, it does not have a significant amount of overhead. It's less than 1%, it's a fraction of 1%. So it also has built-in integration with JRocket Mission Control and replaces the JRA recording and latency analysis tool capabilities that were in previous versions of the JRocket Mission Control. It not only includes data from the JVM, but also from the WebLogic Diagnostic Framework and the Fusion Middleware Dynamic Monitoring System, which allows you to get events for ADF, Web Center, and SOA Suite applications. The Flight Recorder is intended to be a non-intrusive when it's enabled, and to provide diagnostic information in production systems. You can adjust the level of data that's generated for capture higher, but this will result in an additional overhead. The JRocket Flight Recorder is not designed to keep a very long history, so days or weeks, and it is also not designed to capture very large event payloads or high volumes of events. It's also not a replacement for debug logging or server logging. We have engineered the integration of WebLogic and Flight Recorder to be able to view and correlate WebLogic data and events with JVM events that make problem identification easier. And we have instrumented WebLogic to generate Flight Recorder events and have added a custom WebLogic event viewer in the JRocket Mission Control. We also wanted to make it easy to configure and use. It's available out of the box, and it's easy to adjust the volume of events that are generated. We also wanted to be able to leverage the diagnostics in WebLogic server in order to increase the usefulness of the flight recorder. So we have added the ability to dump a flight recorder dataset as a result of a watch rule being met using the WebLogic diagnostic framework in WebLogic. The WebLogic diagnostic flight recorder events are automatically throttled when the system is under stress or under load. The algorithm that implements this throttling uses two different measurements, and there's caps associated for each of these criteria. Currently, it's at 128 requests per second and 800 events per second, respectively. When these caps are exceeded, requests are sampled at a rate that is intended to keep things within those thresholds. So basically, when your system is under load, the flight recorder adjusts in order to reduce the overhead. It's also very easy to configure the WebLogic diagnostic framework event volume at runtime, and I'll show you how we can do this in the demo. There are 4 levels: off, which is the default, low, medium, and high. We consulted with our developer user groups and support organization in order to come up with what we feel is a good segmentation of those events. In many cases, customers will enable the WebLogic diagnostic framework at high in development and low or medium in production, and they are comfortable with that small amount of overhead due to the value that Flight Recorder provides. Here's some of the events that are generated at a low volume. You will see here events for EJB invocation, JDBC statements, servlet invocation, web application load and unload, web services, JAX RPC request and response, and JAX WS request and response. In many cases, this information is sufficient to identify the area or areas for further investigation if you're having a performance problem. And as you go up to the medium level, you'll see events for EJB, home, create, and remove. And this is useful if you're doing a lot of remote EJB invocation. More detailed JDBC connection information, and more detailed servlet information. With high, you'll see even more events such as JDBC transaction information, JTA transactions, and more detailed servlet information, and the stack traces and user IDs for all of the requests. We have also integrated the flight recorder with WebLogic diagnostic framework such that you can capture a flight recording dataset as the result of a watch alert using WebLogic diagnostic framework. We also provide integration with the remote diagnostic agent that our support organization can use to capture JFR events as well. So there is an experimental plugin for mission control called WebLogic Experimental Plugin, and what it does is it provides a tab group and filtering of events that are generated in the flight recording data set that are specific to WebLogic. And we'll cover this in the demo, so I won't spend too much time on it now. Here's a quick screenshot, and basically you'll see that it gives you the option to choose WebLogic on the left side, and then you get a set of tabs at the bottom that are specific to WebLogic areas of concern. Next, let's cover some of the areas of WebLogic that you will likely tune, that is kind of low-hanging fruit, where you should look first to make sure that you have WebLogic tuned appropriately. Here's what we'll talk about: the number of JVMs per machine, threads and work managers, JMS, JDBC, and EJB. So with Java, there's obviously a timeless battle with garbage collection. We reap the benefit of not having to manage our own memory and deallocate memory, but then we have to put up with the garbage collection. So there's a concern of how do you slice and dice your CPU and memory. Do you go with more JVMs with a smaller heap, or do you go with fewer JVMs, each with a bigger heap? Of course, if you choose a bigger heap, then you're going to have longer pause times for garbage collection. And ultimately, the approach that you take depends on your application and whether or not you can tolerate longer garbage collection times. In many cases, when I've gone to customers in the past, before I worked for Oracle even, I've seen them have very large machines and only run one managed server on those machines. One of the customers that comes to mind had a 16 gig quad-core dual CPU configuration, and they were only running one managed server on the machine. And then when they were using Load Runner to do their performance testing, they were wondering why they were only utilizing 10% of the CPU, and they thought that was a problem with the way they have done things. And the answer was, well, yes, of course it is. You've got a good 10 gigs of RAM most likely that you're not utilizing, where you can be running additional managed servers. So in most cases, especially with the standard servers that you find in enterprise installations today, probably going to have 8 gigs of RAM at a minimum, and they're probably going to have dual or quad core CPUs and between 2 and 4 CPU sockets. So in most cases in production systems today, you'll find that you will get better performance and better system utilization if you run multiple managed servers on a physical machine. So in this example, we have an 8 gig server, and I wouldn't say it's over allocated, but I would say it's fully allocated to run multiple managed servers on each one of the machines. Of course, you want to leave some storage left over, some RAM left over for your operating system and additional programs that you may be running on the machine. But really, if you're not using the RAM, then chances are you're not making the most out of your investment. So looking at threads and work managers, back in WebLogic 8.1, you could define explicit thread pools that maps to physical threads that are running in the system. With WebLogic 9.2 and higher, we have the concept of work managers. And it's a best practice to define a work manager for each of your applications using the dispatch policy in WebXML or the WL dispatch policy in WebLogic.xml. And then WebLogic will self-tune the work managers for the best performance. So you don't have to allocate more threads than you think that you need. You can leverage the algorithms in WebLogic to do that for you. You can also define context classes for prioritizing requests and the minimum and maximum number of threads that you want to associate with a given work manager. Also, if you have a multi-tiered architecture where you have WebLogic server for different classes of web services, for example, you really do need to look at creating work managers for your applications. Because if you have a request coming into the WebLogic server domain, and then WebLogic server makes a web service call over the network back into the WebLogic server domain, then you can get a nasty situation where you reach a temporary deadlock with the number of threads that are available in a WebLogic server instance. And WebLogic server will respond by adding more threads, and then the situation will be cleared. And if the deadlock will be cleared. And if this presents itself multiple times, WebLogic will keep adding threads until you reach the maximum number of threads that can be supported, or you run out of memory. Chances are you'll run out of memory first. So by simply segregating the services that you have, whether it's in the service bus or the WebLogic server layer, you can get around that. So not only is it a best practice, it really is a good idea to add work managers for each of your applications. In addition, just because you have defined a work manager in your WebLogic XML or in your WebXML, it doesn't mean that you have to define it in the WebLogic server. If the specified work manager is not found, it will default to use the default work manager. And then later, when you do your performance tuning, you can create work managers and assign them to your applications and restart the server without having to redeploy or change your applications. So give you an extra lever to pull if you need it when you're doing performance testing and tuning. When we look at JMS, there's a few different areas where you can look for performance tuning. Load balancing is enabled on default by connection factories, but server affinity is not. And if you want to distribute all the messages evenly across your system and have JMS messages go on the wire to go to a different server, then you probably want to disable server affinity. So if you have small messages and you don't have low latency messaging requirements, extremely low latency messaging requirements, then you probably want to disable server affinity, which will spread out the consumers for distributed destinations and producers for distributed destinations more evenly across the cluster. And then if you look at persistent storage for your JMS servers, the file stores typically offer the best performance, but JDBC stores offer more ease of failover. So if you're using a file store and you need high availability, it's best to have that store or the file or that directory on shared storage, such that if you can migrate the JMS server onto another managed server if necessary. Also, one of the differentiated features for WebLogic is the distributed destinations that we offer for JMS queues and topics. And this is the concept of being able to define multiple physical JMS destinations and be able to access them through one JNDI name that's the same across all managed servers in the cluster, and that goes for topics and queues. And if you're not leveraging these, you're doing messaging within your applications, you should really take a look at them, because it does allow horizontal scalability for your messaging infrastructure. And then when we look at JDBC, I find customers installing applications that don't use JNDI data sources, and I would advise strongly against this. You want to be able to control the number of threads that you have in your WebLogic server instances and correlate them to the number of connections that you make available to those threads. Ideally, you want a one-to-one relationship between the number of threads and the size of your connection pool, such that if a thread needs a connection to the database, it doesn't have to wait. You can limit the size that the thread pool will grow to by associating it with the connection pool, such that the number of threads will not exceed the number of connections that you have available for the database. In addition, in most cases, it's optimal to set the maximum size to the initial size and disable shrinkage of the connection pools. And what this offers is less latency for handling peak loads. So if you get a backlog of threads that need connections and you've not met your connection pool max, then there's obviously time associated with creating a connection to the database. And ideally, you want to minimize this time and do it all up front when the server starts, such that you can handle peak load very quickly and respond to changes in load very quickly. In addition, you want to probably look at the prepared statement cache for your connection pools and increase it to the point where you have at least a 90% hit rate, if not higher. And if your applications are not using prepared statements for custom JDBC that you may be doing, then I would strongly advise you to go back and look at your code and see if you can identify areas where you have highly parameterized database queries that you run. You'll find better performance if you use prepared statements. Finally, before we get to the demo, I want to call out a couple more common application mistakes that I see. It's good to have properties to configure different things in your application, but it's not good to hit the properties file for every single request that comes into the server. This results in poor performance and poor scalability because it's doing file I/O for each request and it doesn't scale very well. So I'd advise trying to store your properties in a database and/or caching them in the JVM. In addition, when you do XML parsing, you don't want to create a new JAXB context for each parse event. Rather, you're better off creating one singleton context and then reusing that. And when possible, try to minimize the number of session variables that you use. And when you're done using a variable and you don't need it anymore for the rest of your process or the rest of your session, go ahead and set it to null or clear it out of your session. Next, let's see how to enable the default recording for JRocket Flight Recorder and enable the management port or the management console port on the managed server for JRocket Mission Control. So I'll find it under servers and then the server name that I'm using. And I'm using the node manager to start and stop my servers. So I can go under the server start tab and add additional arguments for starting my server. Here I'm specifying X management to enable the management port. I'm enabling auto discovery so I don't have to put in the IP and port of the management server or the management connection. I'm disabling authentication, enabling remote connections, and disabling SSL. I'm also using the flight recorder option, specifying the default recording to true. So go ahead and save this, and then I'll start my server. take a look at my server log here, and we'll see that the server is starting. And we'll come back to this. So next what we want to do is enable the WebLogic Diagnostic Framework volume. So here you'll find it under the server name, under the server configuration, under the General tab. We'll see the diagnostic volume here is off. So what I'm going to do for this example, since we want to get the most information possible, is set it to high, and then save that. And this is a runtime setting, so even though my server is still starting, I can specify this and change it at runtime to get a different volume of data. Next, let's take a look at SoapUI. SoapUI is the tool that we'll be using to generate the load for this session. SoapUI is a good tool for doing both load testing and functional testing for web services. If you have a UI that you can use, then something like LoadRunner is pretty handy, but if you want to do specific testing of services, something like SoapUI will be very useful. It's free. There's a free version and a paid version, a professional version. Many of the options that you would need for just basic web service testing are available in the free version. It's a tool that I really like to use. So what I'm going to do is create a new SoapUI project, and then I'm going to add my WSDL and WADL files from my different services. So if we look at the URLs that we need to use, we'll see that for my JAX WS services, I specify my shipment endpoint and then append $WSDL. So let's go ahead and add that WSDL to the project. And we'll see that it imports the port and creates request and response examples for each one of my operations. Let's go ahead and add the REST service as well. The endpoint for the REST WADL file, you'll find it under the deployment name, so the WebLogic deployment name, and then the servlet name, and then application.wadl. So I'll go ahead and add this WADL to my project as well. In here, what we can do is use the default request that gets generated. I'm going to insert my shipment object, my example shipment that I use. And then when I execute this request, we'll see that it's running, and here's my response. And I know it's successful because I get an ID that's generated from the database on my response object. So now what I can do is do the get shipment, specify my, let's go back and get the ID. I can specify that on my requests, and now I can execute my service and get my response here. So this is good for one-off testing or individual testing of a specific case that you want to do manually. But you can also create test suites and test cases using SoapUI. So what I'm going to do is take this request and add it to a test case. For the example, I'm going to accept the defaults. And then we'll see here that I have a test case dialog, and then I can hit the play button, and I see green here for the request that was successful and passed validation. So this is useful if you want to do multiple requests in a row. For example, create a shipment, then get a shipment, or then take multiple steps to do that, to validate your request and response or your different test cases. But what I'm interested in is creating a new load test for this test case. And here what I can do is very simply start a load test using the request that I just edited and accepting some of the defaults to place load on the server. So here we'll see that the default is to use 5 threads. So that means there's 5 threads executing requests or executing the test case, and then multiple steps within the test case. Defaults to have a test delay of 1 second per execution with a randomization factor of 0.5. And it defaults to run for 60 seconds. You can also choose the number of runs per thread and the total number of executions that you want for the test case. And while it's running, we'll see that you can look at the minimum response time, the maximum response time, and then the average for each individual case. Here we'll see that the average is around 3 milliseconds. we'll see that I've been able to execute 320 so far. You see the transaction per second and the number of bytes that have been transferred as a result of the individual step and then the overall step. So here, for this example, I was able to execute 392 in 60 seconds with an average response time of 3.17 milliseconds. Now, let's take a look at how we would test a REST service. We'll see when I import my WADL, it has my different resource URIs. I'm going to also execute a test here to retrieve my shipment. We'll see that it uses the template, the URI template, and pulls in the properties here that I can specify. So now when I execute this request, we'll see that I get my JSON back, and it's the same object. But SoapUI also takes the JSON and puts it into a simple XML format for readability and XPath purposes. So, like I did with my JaxWiz service, or test case, or request, I'm going to create a new test case with my REST service. Here, same thing, I have my test case, and now I'm going to create a load test out of this test case. And let's kick this off. So again, I'm using the default parameters, which are run for 60 seconds, 5 threads, test delay of 1 second, plus or minus 5%. So again, we can see the minimum response time, the maximum response time, and then the average response time. So here, we're about halfway through, and we can see that the average response time is dropping and probably end up around 2.5 milliseconds or lower. We can also see the count of the operations that's being executed and the number of bytes. And as we were saying when we're comparing REST with SOAP, one of the big differences is the requirement for XML in the request and response, no matter how complicated the request object is. So here, I'm just hitting a URL for my REST resource, and there's actually no payload to the message. So in this case, I was able to execute 394 operations, but the number of bytes that I have for my REST service is 358K, approximately, versus 875K for my SOAP service. So we'll see that the number of bytes that are required for executing REST services is much lower, which makes it ideal for very small objects with high volume, throughput, and low latency. Next, let's take a look at the test case that I've created to test a more complete example. Here, I've created a test case that has several steps. I'm generating an external ID using Groovy. I'm transferring the result of that script into a property that I can access. And then I'm creating my shipment using the external ID. I'm transferring the properties, the parcel IDs, the external ID, and the ID of the object that gets created using XPath. And then I am sending a series of parcel log events and then checking the parcel log after each one of them. And I'm doing that for both of the parcels that are on the shipment that I create. So when I run this, we'll see that it has multiple steps. And when I run the test case, we'll see that it is successful. So it's always a good idea to run the test case before you try to use it for a load test, because you want to make sure that it's going to be successful. For this example, in order to generate an amount of data that will be interesting for the demo and for the JRocket flight recorder, I'm going to run this for 300 seconds with a test delay of 500 milliseconds between each execution, and I'm going to use 10 threads. So we'll see that it gets off and running, and then we'll switch over to the JRocket Mission Control console. And it doesn't update the results until at least one has completed. So there we go. So here are my first 10 that have come through end to end, and we see that it's off and running. So now let's switch to the JRocket mission control. We'll see here that my managed server has automatically been discovered, and I'm going to go ahead and start a console here so we can see the data in real time. So I'm going to change the zoom level, zoom out a little bit, and we can see in real time that we can have a view into the amount of Java heap that's being used, the CPU usage of the JVM, and then other information about the memory as well. Each one of these graphs is created using mbeam properties. So if you want to overlay different data on a graph that already exists, you can choose something like the pause time target, and you overlay that on any graph that you want, since it's all being generated using mbeams. There's an mbeam browser that you can use to look at different settings or different runtime settings. And we can also look at the runtime information, such as the JVM version, the number of CPUs, the number of threads, which is interesting, and the memory statistics, such as the free physical, free heap. And then we can look and see what our threads are doing. So here, I can see in real time what my threads are doing for each sample. And we'll come back to this example, but I've put in a sleep statement into the code so I can create delays and essentially create a bottleneck that we can look and tune at later. You can also do profiling of methods to see how many invocations there are and the time per invocation. You can look at exceptions that are being generated, and you can also execute diagnostic commands, such as starting a recording, dumping a recording, and so on. So if we go back and look at the CPU, I have my test that's been running for about 2 minutes. So what I want to do now is dump the default recording that's been going on with JRocket, with the flight recorder. And we'll see that in this case, we can take up to the last 15 minutes of the recording and get that data. And this is very useful because in many cases, problems don't manifest themselves on demand. So it makes it hard to track down problems. So if you have the default recording running for the flight recorder and you experience a problem, then you can go back in time up to 15 minutes and get the data that corresponds with the time frame of that problem. So if it happened within the last 15 minutes, I can gather that information. So this is how you would dump the default recording, but what I actually want to do is go back and pull a recording that I've done previously that shows a lot of great detail about testing the JAX-WS and JAX-RS services that we have in the project. So let's take a look at the recording that I did earlier actually, which includes load tests from both the JAX-WS and JAX-RS endpoints. So here we can see the CPU usage and heat usage. We can also see information about the system, so I can see I'm running Oracle JRocket and then the version. I can see the application arguments and then the command line arguments as well. Information about the recording, and then the system properties for Java, and then the environment variables for my operating system and information about the hardware as well. So you can see how this will be very useful for the Oracle support and helping you diagnose problems. Here we can see information about the memory, where I have my initial heap size and then my maximum heap size, and the total number of garbage collections, and information about object allocation. Here I see kind of general information about the garbage collection, the graph including information about the individual garbage collection events. I can click on an individual event and then see details for that event. Get some advanced information about garbage collection. I can look at memory allocation, so I can see that here the largest contributing class is an array, and then we can drill down and see where that's coming from if we want. Next, let's take a look at the code options. This gives us a view of the hot packages that are being where the code is being executed. And here we can see that it's primarily between allocating memory and waiting for locks. We can also see hot methods here, which are the methods that are taking the most time. In this case, we have the allocate object and then wait for release for a lock. Then I can see the exceptions that are generated if I have exception profiling turned on. Then information about just-in-time compiling if I have that as well. So here, we'll see here, this is when I started the recording, or this is when actually I started the server. So we won't be able to get CPU data, obviously, before that. We can look at hot threads. So we can see here the default message listener container. So I'm sending in a fair amount of JMS messages. So we can see that those are the top 2 threads that are taking time in the server. And then there are other threads here that are likely for the web service request that I'm sending in. Here we can look for items of contention, and I intentionally put one in, which is a string contention here, where I am forcing a sleep on the parcel service on these 2 EJBs in order to get some variation in the time, and also to show that it can find contention for locks. We can also see the other areas where there may be locks or contention for locks. And we can also look at latencies. So here we see there's a lot of Java wait events. And we can do use lock profiling if that's turned on. Since this is very heavy, it's not turned on by default. So next, let's see what we can see about the WebLogic information. There are 2 tab groups down here. One is for events, and you can choose to enable different events for the Events tab, and then look at different logs for those, and see graphs for threads and contention for the events that are raised by those threads. See information about different threads. So here we see that the default message listener container thread had 8,000 samples. So it's likely that about 8,000 or more JMS messages went in. We can see the histogram of the different types of events. So let's actually take a look at the WebLogic tab, and this takes the events that are specific to WebLogic and then puts them in tab groups that are easy to look at. So here we can find information about our web services, and we can see that this combined web service is the one that is taking most of the load. We have information about servlets. So since I'm running the JAX-WS services and the JAX-RS services, we can see here that all of the JAX-WS is going here. A lot of the JAX-RS is going here for creating shipments. And then here we have the servlet URIs for manipulating the objects for the parcel log. Next, we can take a look at JMS, and we can see the number of consumers that are on the JMS destinations, and we can see when those consumers were created on the destination. We can look at EJBs. We can group them by applications. We can look at the components within the applications, individual EJBs, and then the individual EJB methods. So if I use EJBs and then click on each individual EJB, I see the methods that were invoked and the percentage allocated to those for that EJB. So here for the parcel manager, I see that it's split between adding parcel log, updating the parcel status, and then retrieving the parcel log, and that corresponds with the methods that I have in my load test. Here I have the components, so looking at the domain services, I see that I have my 2 entity managers and how a split is done there. Finally, here I have my database tab where I can see the SQL that is being executed during my recording. And what you can do here is figure out what SQL is running and then see how you can tune that SQL in the database. Here we see that the primary SQL that is being executed is retrieving the parcel log event. I'm also inserting a lot of parcel log events. Here's my JMS store, my persistent JMS store, JDBC, so it's writing every message that comes in. I'm updating the parcel, and then my inserts for creating address objects and shipments. Finally, one thing I want to point out here for the WebLogic tab is the execution context IDs. And what you can do here is find one that is interesting. So we can look at this and see there's a web application and it's doing a lot of EJB invocation and JDBC. And then you can see this execution context is doing JAX WS. And then you can scroll down and see the individual requests that are going through the system. And here, for example, this is the REST shipment where I am updating a shipment or retrieving a shipment. So what I can do is actually add this to my operative set. Now the ECID is in my operative set. So now I can take that, use that context, look down on my other events, and only show the events for the operative set. So now this event log is being filtered for my operative set, which is that one invocation context. I can see the threads that are associated with that. So there's one thread. I can see the traces if I have that enabled. And I can see the graph for my operative set, which is that one thread. And what we can do here is zoom in and see the different events for that thread. So here we see that there's no events for this portion, and then during this time is when it's invoking my EJB method. Given an execution context ID, you can go through and filter out the events. You can get a lot of data like how long the servlet request took, how long the JDBC took, and so on. So it's a pretty powerful tool to use. One of the most valuable use cases for this is finding an execution or an invocation that took a long time and finding the execution ID and filtering for that execution ID, and then you can find where the time was taken for that invocation, what took the most time and what was contributing for it being a long-running process. Thanks for joining us for the last of our webcast series. Please let us know if you like the series, if you want to see more like this, or how we can improve it in the future. And now we'll open it up for questions. Thanks.